Alright, now that we've got our data into a state diagram, we can take it and start to move into what's called a transition table. That's what's in front of you right now. The first thing that you're going to do is we're going to take a look at down the left-hand side here, we have state 1, state 2, state 1, state 2, state 3, but we see that there's two of each of them. We'll explore all of that, what that's all about in a second. In state 0, it makes sense for our QA and QB to be 0. We just did that in our diagram. In state 1, it makes sense for them to be 0, 1, state 2, 1, 0, and so on down the line. So the reason why we have two state zeros is because there's two things that we can do with enable while we're in state 0. We can not press it, or we can press it. Same thing in state 1, we can not press it or press it, and the same all the way down the line. And as you see now, we have essentially counted in binary from 0 to 7. Even though we have only 4 states, we've got binary written from 0 to 7. The next thing that we're going to do is we're going to take a look at what happens when we have those inputs. What state are we headed to? So think about those as those red lines on our previous diagram. So I'm going to draw them in red over here. So when we're in state 0 and we don't press the enable button, our QA and QB are going to stay the same. When we're in state 1 or state 0 and we do press the enable button, we're going to move to state 1. We want our QA and QB to be 1. State 1 and we don't press it, we're going to stay the same. And state 1 and we do press it, and we're going to move to the next state. And so I think you can see the pattern that develops here. Finally, when we get to the end, we're in state 3 and we finally press that enable button, we're going to move back to state 0. So we're going around in a circle there. For the next step, you need to take a look at what an actual state a state circuit looks like. And here we have two flip-flops, and we can see we have QA up here on top and QB down here below. And it's feeding into a number of outputs here. Here's our outputs. That would be our encoded binary outputs. And a lot of this is getting passed back through into our data in. So we're taking data and we're passing it back into the very beginning of our flip-flop from what's coming out of it. So it's helping us transition from one state to the next. So that's what this next set of columns is about. DA and DB refer to what are the data in that we'd like. It's an output, but it's also an input. So it's over here in the outputs because the outputs depend on what the inputs are. So what we're going to find is if we want to be going to state 0, we're going to have a 0 and a 0. And if we want to be going to state 1, we're going to have a 0 and a 1. If we want to stay in state 1, we're going to have a 0 and a 1. And again, you can see the pattern that develops here pretty easily. It's just the same as the previous two columns. Finally, we're going to encode our outputs. So our first number was going to be a 4. And so in state 0, we're going to want a 4. So for state 0, for both of those, we want a 4. So we're going to encode that with binary of a 0, 1, 0, 0. And we want a 4 for all states of 0. Yes, we're going to move on to those other states, but for when we are in state 0, when we're in state 0, we want to make sure that we have a 4 in there. When we're in state 1, we want a 6, so 0, 1, 1, 0, 0, 1, 1, 0, and then continue on. So, let me see, we're going to a 9 next, and then finally to just a 1. And that's how you complete your transition table. Next, we're going to have to take this data and translate it into some K-maps so that we can so that we can actually make our circuit.